So here we are. Chapter 1, and we're going to look at linear motion. Okay. So to describe motion, we need its basic parameters or its basic characteristics. So to describe motion, we need its basic parameters. We're going to need distance, time. We're going to have to talk about speed, which is embedded in velocity. And we're going to have to talk about acceleration. So when you look at these parameters, you're an expert at all of these. You're definitely an expert at distance, time, speed, and acceleration. You've been doing it your whole life. So what I want to do with these basic parameters here is that I want to take your everyday knowledge of motion and put it into the language of physics. Why do we want that? It turns out everyday language is sloppy. It's not precise enough. We need something to be more precise. And in the end, when I say I want to put it into the language of physics, this language of physics is a picture. And this picture is known as a motion diagram. So in the end, once we get that motion diagram down, you'll see you'll have deeper knowledge of what motion is, and you'll be able to analyze it more consistently here. So let's go move in that direction here. So what I'll do here is that I'm going to start off with some of the basic definitions here. I want to start off with distance, which you already know. And I want to talk about time and speed. Again, I don't have to tell you what these things are. You already know what this is here. So here we go. So the most basic definition that we use a lot here is speed. I don't have to tell you what speed is, right? Speed is a measure of how fast something moves. Right? It's how fast something moves. Well, what is this in the language of physics? So the way we see speed is in the car. And what we talk about is we talk about miles per hour. So when you look at miles per hour, what it really means here, right? So it means miles per hour, which really means miles per hour. And so what you're seeing here is that miles is, of course, a distance, hours a time, So this tells us here that speed must be distance divided by time. So right away, we have now defined speed in terms of an equation here. But that's what miles per hour means here. So let's look at this in terms of examples to make it real clear. So as an example here, we know 60 miles per hour is faster than 20 miles per hour. Of course we knew that. But the question is, what do I really mean by that? Well, what we're seeing here is that it writes something like this here. If I have 20 miles per hour, then what this really means here is that I'm going 20 miles in 1 hour. And if I compare this to 60 miles an hour, this is 60 miles in 1 hour. So what we want to do here is that the thing that I want you to pay attention to here is look at the time in each of these situations. The time is exactly the same size. So look what I'm going to do here. I'm going to write time here, time here. And what you're seeing here is that these times are exactly the same size. So I've written them on purpose to be the same size. But now let's look at that equation speed here. If I compare 20 miles to 60 miles, that distance that we covered is a small distance. Whereas the 60 miles is really what? Is a big distance. So why did the car traveling 60 miles an hour have a faster speed? Because it covered more distance. Therefore, what you're seeing here is that this is larger and this is smaller. So that equation is guiding my thinking. The reason why 20 miles an hour is smaller is because the distance is smaller that it covers in that amount of time. 60 miles is faster because the distance is larger. So now what we want to do here is that we want to redefine our equation because we don't want to be writing big words because that's not what science does here. So what we're going to do here is that we're going to rewrite the speed equation. So the way we write this thing here is we define the Greek symbol. So there's a capital, wow, I keep spelling capitola. Wow, I for the life of me, I can't. There's a Greek capital letter called delta. And that delta symbol looks like this. This guy in science means change. So if I have a change in distance, we write it as delta x, where x here is distance. And if I want change in time, we write delta t, where t here is time. So what we say here is we say the following thing. So if we rewrite the speed equation, then I know that speed is distance So we rewrite this as delta x over delta t. That's how we redefine our equation right there. So now, what does that mean? So if I look at my 20 mile an hour, right? So if I have 20 miles an hour, we know that this is 20 miles per 1 hour. So then we know that our delta time looks like this. And if I look at 60 miles an hour, we know that this is 60 miles in 1 hour, and we know that the time here is the same. So what's the big difference between these two? Well, one of these has a small distance. We didn't cover very much distance. The other one has a huge distance. And as a consequence, we say that this has a high speed, whereas this one has a lower speed. So what you're seeing here is what we're doing here is that when we write small letters, it's a slow speed. Here we write large letters. It's a fast speed. And that's what I mean by the equation being a picture. So moving on here, let's get to the next piece here. Speed is an incomplete statement. Velocity is the correct term. And so what we find here is that velocity is represented by a vector. And a vector is nothing other than an arrow. So velocity is represented by a vector, and it has two characteristics. So all arrows have two characteristics. So here's the thing here. Well, what you see with an arrow is that it has what? It has a direction, right? The arrow points in some direction. And the other thing that's important here is that the arrow has a length. Mathematics, we don't call them lengths. Sometimes we call them lengths. It's more common to call them a magnitude. So the length of the arrow is called a magnitude. So what we say here is that vectors have magnitude, which is equal to length, and they have direction. So here we go. So what we're saying here is that our definition goes something like this here. What we say here is that velocity is a vector and is defined as this. So typically when we write velocity, we replace it with the symbol V. Why? Because it's easier. And so what we're seeing here is that the velocity has a magnitude, What's the magnitude of the velocity? It's speed. And what is speed? It tells us about how fast something moves. And it also has direction, which tells us which way. So when I'm looking at velocity, the speed here is what we call the magnitude of the velocity, and the direction here tells us which way we're going. So the definition of velocity is that it has two pieces here. Okay, it has two pieces. So now what do I mean by this? So I'm going to draw a picture. So my picture here is that I'm going to set up a coordinate system that looks like this. So this will be the east direction. I'm going to move this over here a little bit. And this will be the west direction. And so what I can have here is that I can have various velocity vectors. So our previous example is that we had a velocity that was 20 miles per hour. So what do I mean by that? So the first thing that I'm going to do here is that I'm going to look at the length. So I'm going to look at this length of this vector, and what you're seeing here is that I'm going to make this 2 squares. So the length of this guy is 2 squares. So here, 2 squares equals 20 miles per hour. But there's another piece of information here. You could see here, so if I was to write the velocity vector, what this really tells me is that this thing is 20 miles per hour and it's pointed in the east direction. So note, I got to give a magnitude and I got to give a direction. Now, the other car that we had was traveling at 60 miles an hour. So that means if 2 squares equals 20, then 60 would have to be 6 squares. So then if I have another velocity, let's go like this. So that's 2, 4, 6 here. So if I look at this length here, 6 squares implies that the length of this thing is 60 miles per hour. So this should be, right? In this case, we could say here is that 6 squares equals 60 miles per hour. But the velocity vector, that's the speed. The length of this thing is the speed, but the direction should then say 60 miles per hour, traveling in the east direction. That's the velocity vector. So if I was to look at this, this is the velocity. This is the velocity. So that's what that thing is telling me right there as far as speed and direction.